Hello and welcome to our next lesson in which we're going to learn why the straw lab works the way it does and how to apply the concept of equilibrium to reactions and how that's going to tie into both kinetics and thermodynamics. Now, this might go a little long, so I'm going to try to work as quickly as I can, not to keep you too long, but we do have a FET that we're going to look at, and so that might make me take a little longer than I usually do. All right, so we're going to start off with the concept of equilibrium coming from looking at reactions that, just like the straws, can go in the forward or reverse direction. And so we call these reversible reactions. And these reversible reactions are always going to be denoted by two arrows, one pointing in the forward direction and one pointing in the reverse direction. And these two arrows, these two directions indicate that the reactants are always forming products, products are always forming reactants. Another thing we're going to do is that we're going to assume, for the sake of kinetics, that the forward and reverse reactions both occur in one step. And that way we can apply rate laws to both the forward and reverse direction. So let's go down and see what's going on. Let's look at these graphs first. In these graphs, in graph number one, we're going to start, and both of these, we're going to start with products. And I'm sorry, starting with reactants, not starting with products. And as the reaction proceeds, the reactants are going to decrease, and they're going to reach some concentration, just like the straw lab did. And as the products are formed, they increase. And at some point, we're going to reach a place where the concentrations of the two reactants, of the two products and the reactants, stop. And that's going to be the equilibrium. Now, the difference between graph number one and graph number two, I'll get to in a moment. And then graph number three, I will get to again in just a moment. So let's see what's happening with the reactions as we're going through this process. So for graph number one, and this works for graph number two as well, but graph number one, the rate law for the forward direction. The rate law for the forward direction is always, or for either reaction, the rate, and I'm going to put a little sub f here. So that little subscript f means the forward direction is equal to, now we're going to have a rate constant for the forward direction. So there's a K, I'm going to write it up here on the reaction up above, as a rate constant. And then we have the concentrations of the reactants. And again, if you had any coefficients, you'd have to put them there as well. So this is the rate law for the forward reaction. Now, initially, the rate for the forward reaction is going to be fast. So if you look up on the graph number three, we'll see that in the forward direction, the rate starts off high. And that's because there's a lot of reactants. In fact, we have all reactants. And so Kf times the reactants is large. And the rate of the forward reaction decreases because as the concentrations of the reactants goes down, you have fewer collisions, and so the rate is going to go down. And so initially, up on graph three again, the rate of the forward reaction starts off high and drops down as we're moving along. Now, switching over to the reverse reaction. So now we've got to worry about what's going on backwards, because now those products can go back and reform reactants. So the rate of the reverse reaction is going to mirror what's going on in the forward reaction. It's a reverse reaction, so the rate sub R for the reverse reaction is equal to the K sub R. Let's write that up there. K sub R up on the reaction up above for the rate constant for the reverse reaction times the concentration now of the products, which are technically the reactants in the reverse direction. We're going to find that as we get into this equilibrium, you're gonna see you can flip things around and making products reactants, reactants products. Everything is fair game at this point. So initially there's a slow rate. Actually, there's zero rate. Initially, the rate is equal to 0 for the reverse reaction because there are very few, let's call it 0, products. So Kr times the products, concentration of the product, is very small. So up above, we can see we're starting down close to 0, if not 0. And then as the concentration of the products increases, the rate in the reverse direction has to increase. More product means more collisions, means higher concentration, and so forth. And then what happens is as the rate of the reverse reaction increases, and the rate of the reverse reaction increases, the rate of the forward reaction decreases. At some point, the two of them come together, and they become equal. And when you reach that point, that's when you have equilibrium. So in equilibrium down below, we're going to write for the forward and reverse reactions as the rate F decreases and rate R increases, eventually they become equal. And so that's where we have equilibrium. Now, you can't generally see these rates happening, and especially if the rates are not changing anymore, you're never going to be able to do something like the iodine clock lab here because you're never going to get to that point where something's going to change color for you. So we're going to look at the concentrations of the reactants in the products as an indication of equilibrium. And here's what's going on. Since the rates are equal, and this is just like, think about the straw lab, the same amounts are produced in both directions. And so we got, every time we make a reactant from a product, we make a product from a reactant, and the concentrations don't change. Now, the difference between graph 1 and graph 2 is whether or not we have a faster, a reaction that's inherently faster in the forward direction or in the reverse direction. So at equilibrium, the rates are going to be the same, but in graph number 1, we notice that the concentration of the reactants is lower than the concentration of the products. So what we're going to do is let's set the two rates equal to each other. So the rates are equal to each other, which means that the Kf times the reactant concentration is equal to the Kr times the product's concentration. Now that looks like a nice inverse relationship to me. So since the inverse if the concentrations of the reactants is less than the concentrations of the products, then the forward rate constant, in order to make this up, K in the forward direction, has to be greater than the K in the reverse direction. So this is a reaction that inherently is faster in the forward direction. The rate constant is faster in the forward direction, But when we reach equilibrium, the two rates, not the rate constants, but the two rates, when you include the products, include the concentrations in there, become equal to each other. In graph number 2, let's switch colors. Graph number 2, we're going to start from the same process, but now notice in graph number 2 that the reactants have a higher concentration than the products. So, as in C, letter C up above, if the concentrations of the reactants are greater than the concentrations of the products, then the reverse must be true of the rate constants. Then the K in the forward direction must be less than the K in the reverse direction. And so we have less favored, let's call this less favored in the forward direction. Whereas for C, we were less favored in the reverse direction, or more favored in the forward direction. So we're going to see that reactions can be favored in one direction or the other. No matter which way that they're favored, we're going to find that this equilibrium is what we call a dynamic equilibrium. Now, dynamic means that something is changing. There's something going on. It's a dynamo. Things are happening. This is contrasting to, say, a static equilibrium. A book sitting on a table is in equilibrium. All the forces are equal. You maybe learned about forces in middle school science. The forces are equal, but the book's not moving. Nothing's happening. In chemistry, that's not the case. We have these dynamic equilibrium because the rates of the forward and reverse reactions are equal and greater than zero. Those reaction rates are greater than zero, so they continue. The reactions continue. Now, how do we have some evidence for that if we can't see, as I said up above, you can't see a change going on? How do you know that something must be going on? So we've got this ingenious way of figuring things out, and that is by using what we call radioactive tags. So let's take a system that we want to study, and we're going to get the system to equilibrium. So we start off with this reaction where we've got hydrogen gas and iodine gas in reaction forming 2HI. And this is a reversible reaction. Most of these reversible reactions are going to be simple gas phase or solution phase reactions like this. And we're going to start with 1 mole of H2 gas and 1 mole of I2 gas. We put that into a 1 liter container. So 1 mole each, we have concentrations of 1 molar. And initially, so this is an ICE table in which we're going to track what's happening between what we do initially and what happens eventually to get us to equilibrium. And this change is going to be a crucial thing that we're going to be looking at. So initially, we don't have any of our product. So this is a 1 liter container that didn't have anything in it, evacuated 1 liter container to start with. Now, the reaction occurs and we come to equilibrium. At equilibrium, we find that we have 0.2 molar of each of the reactants and we have 1.6 molar of the product. So what happened? What happened was we lost 0.8 molar. The change was a negative. Changes are always going to have a plus sign or a minus sign on them. In this case, the reactants decreased by 0.8 molar, 0.8 molar. Now, stoichiometry is going to apply here. Notice we have a stoichiometric coefficient of 2 on the HI. For the I and the H, we have stoichiometric coefficients of 1. So that means whatever we're doing on the I, on the H and the I, we have to multiply it by 2 to get to the HI. And the opposite is true. So as the reactants go down, so reactants are going to be negative because we're using them up, we're going to form product. And so this HI concentration is going to increase by double the decrease in the concentrations of the reactants. And so this is going to go up by 1.6 molar. And that gives us our equilibrium situation here. And we'll talk about how to describe that. We'll finish off this lesson with a hint at that, and in the next lesson we'll actually get into the nitty-gritties about describing that equilibrium. Now, suppose instead of starting off with only reactants, let's say we start off with a system that's already at equilibrium. So we're going to put in at the start, we're going to put in our equilibrium concentrations. We're going to have 0.2 molar H2, we're going to have 0.2 molar I2 and 1.6 molar HI. So you're starting off, you're at equilibrium. But instead of regular plain old iodine, we're going to put some radioactive iodine in. That's what the little asterisk here, that's a tag. That means that this is radioactive. Now, if nothing was happening, the iodine, the I2, would stay radioactive and nothing else would happen. But here's what happens. As time goes by, we get that radioactive tag here and here. We get it still in the iodine, but then we get some in the HI as well. And so this is going to be our evidence. But why is this our evidence for the dynamic process? So in order to make reactive HI, radioactive HI, the forward reaction must occur. Otherwise, we're never going to make any HI that has that radioactive iodine in it. So the forward direction must occur. So we're going to use up I2, but we're also going to use up H2 because you can't make HI without using both the H2 and the I2. All right, so we're making the forward direction occurring. However, and then, let's put it a star, radioactive iodine. But if we're at equilibrium, we just said up above that the concentrations of the reactants and products can't change. So we have to keep the concentrations constant. The reverse reaction also occurs. And so here's the dynamic process going on. We have some of the iodine going to the HI going to iodine, some going to HI. And what's going to happen eventually is that the iodine is going to be evenly distributed between the or according to the equilibrium, evenly distributed between the products and the reactants. So hopefully that makes sense to you at this point. Now what we're going to do is take a look at thermodynamically why this is happening. So we talked a little bit about the kinetics. Now we're going to tie kinetics into thermodynamics. And we're going to do that by going to a FET. And I've got the fet.colorado.edu website here. And a FET that's called reversible reactions, which I've downloaded. Unfortunately, this is not one that has an HTML5 version of it. So if you wanted to download this, you could, but you'll have to make sure you have Java installed on your computer. So here is the FET. And what I've got set up here is I've got a reaction which has the reactants on the left and the products on the right are at the same energy level. And I've got a little barrier in the middle here. And what I'm going to do is I'm going to add in 100 molecules of reactant A. Now watch what goes on. As the reaction proceeds, we're going to start making B. And you can see up above that the size of the A and the B indicate how many of each we have. Eventually, we're going to see that we're getting to an approximate equilibrium. Now, it's going to fluctuate. The numbers are going to fluctuate because having only 100 molecules is not a large enough sample size to really prevent that from happening. But if you keep watching, you'll notice that the number of A and B molecules is going to stabilize at around 50 each. A little higher right now. We're not quite at equilibrium. And so why should we stabilize at 50 molecules each? So let's go back to our notes and think about this for a moment. First thing, let's write in. So we have 50 molecules of A and 50 molecules of B. So at equilibrium, the concentrations of A and B are equal to each other. Okay, now just keep in mind that's not always going to be the case. Equilibrium doesn't mean equal concentrations. Equilibrium means constant concentration. Because the concentrations are equal to each other, and at equilibrium, we have to have the rate of the forward reaction equal to the rate of reverse reaction. If the A and B are equal to each other, that means the Kf and the Kr are both equal to each other. And this reaction does not favor either direction. One of the reasons for that is that the EA, the activation energy in the forward direction, what's the activation energy in the forward direction? Well, it's that little bit right here. EA in the forward direction is equal to the EA in the reverse direction. Oh, come on, stop moving around on me. This is why this takes longer than I want it to. And at the same time, the only way for the EA in the forward direction to equal the EA in the reverse direction is for the two levels of the reactants and products to be the same. The energy levels, the potential energy. This is the potential energy diagram. Maybe I should write that on there so we understand. So this is potential energy as we're moving up. So in this case, and this is a delta G we're going to be looking at now, not a delta H. So in this case, now the delta G of the reactants equals the delta G of the product. So the delta G naught is 0. There is no difference between the reactants and products. This is actually a definition that in this case, when you're at equilibrium, so in this case, we're at equilibrium. When we're at equilibrium, the delta G naught is 0 because at equilibrium, the concentration of A is equal to the concentration of B. Now let's go back to our simulation. And why is it saying close window? I don't want to close window. There we go. Let's reset this and start off with, instead of 100, let's start off with 200 A molecules. What do you expect to happen? Well, doubling the concentration should eventually end up doubling the concentration. Doubling the concentration of A should end up doubling the concentration of B. And you can see that the concentrations are both tending toward 100. And eventually, I don't want to take up too much time here, but eventually if you play around with this, you'll see that you do get down to 100. So let's go back here and let's write in that the concentration of A is 100, concentration of B is 100 molecules. And now we can write a ratio of the concentration of A and B. Or let's put B up on top since it's the product. So the concentration of B divided by the concentration of A, it was 50 over 50 or 100 over 100. Either way, it equaled 1. All right, let's play around with our thermodynamics a little bit. And as we play around with the thermodynamics, we're going to see that we're going to play around with the kinetics. So what I'm going to do is set up this reaction in which I have a negative delta G. So here's my delta G. And let's call it a delta G naught. And so I've got an activation energy in the forward direction that's smaller than the activation energy in the reverse direction. Think for a moment, what do you think is going to happen when A molecules form B molecules and they get stuck? They get into that trap because remember, we're all at the same temperature, and so it's going to take more energy to get over the reverse barrier than it is to get over the forward barrier. All right, so let's go to our simulation and let's reset this. And let's bring this up. I want to bring this up to about 30, a little right there. I'll let go, mouse. And I'm going to bring this up to about 25. And now I'm going to pump my 100 molecules into here. So watch what happens to the process. So we start making our B molecules, and we keep making those B. But notice, it's a lot easier for the A's to get over that activation barrier. This whole thing is at the same temperature. It's not like we have the A at one temperature and the B at another temperature. This is all in one reaction container, and this reaction container is all at the same temperature. So watch the numbers on the A and the B. Previously, we started to even out at 50, and it looks like we're stopping at 50 now, but hold on. Notice that we're getting lower on A and higher on B. So the A is going down. We're about 40A and 60B. And depending on the exact numbers that you end up with here, and the exact height of each of the the potential energy of the A and B, and the potential and the height of that energy barrier, you're going to get a different situation. So in the notes, I've got something that may be slightly different. Oh, look, we're down below 30 now. On the A, we're down to about 22, 23. The B is at about 75. Okay, so at this point, it looks like we're starting to stabilize somewhere around 25A and 75B. So let's go back and start explaining what's going on here in terms of thermodynamics and in terms of kinetics. So if we have 25 A molecules and 75 B molecules, that means that the concentration of B is much greater. And this is a product favored. So we say that this is a product favored reaction. Now, by the same argument as before, if the concentration of A is lower than the concentration of B, that means the forward rate constant, Kf, has to be greater than the reverse rate constant, which means this is easier in the forward direction, and it means that it's faster in the forward direction when the concentrations are equal. That's really what the delta G naught is talking about, when the concentrations are equal. So if we were to put in equal concentrations, then the reaction rate in the forward direction would have to be larger. So to have a rate constant that's larger means that you have an activation energy that's lower. So the activation energy is lower than the activation energy in the reverse direction. All right, so this again, this favors the forward direction. So this favors the forward, let's call it the forward reaction. Forward direction is the way we kind of say it colloquially. Now, the delta G we already said was negative. And so this is a reaction that is spontaneous in the forward direction. And that's a delta G not there. In the forward direction, again, when the concentrations are equal. And eventually those concentrations become equilibrium. And as I said, when we reach equilibrium, the delta G actually is zero, not the delta G naught, but the delta G. That's a concept which is a little bit beyond what I want to go to. What about if we put in another 100 molecules of A? Let's go back to our simulation and do the same thing. I guess I want to reset it. I hate resetting it because it takes a little while to get back to equilibrium. But 200. So that's a lot of molecules. And we'll watch as the A reacts to form B and the values come back down, hopefully to the same ratio as before. Now, if the numbers are a little off, don't worry about it. It's really the concept and the idea that at equilibrium, the concentration of the A is a lot larger than the concentration of B. I'm sorry, I got that backwards. The concentration of B is bigger than the concentration of A. All right, so we're tending now down towards, looks like we're going to be getting down 65, 60, sub 60, down towards 50. And there we're heading towards about a ratio of 50A to 150B. So let's go and write that in. We have 50A and 150B. Now, we're going to write this ratio again. And this ratio, if this whole process works properly, the ratio shouldn't depend on the initial amounts. So the concentration of B, why is that coming down like that? Something with this cell B over A. We had 75 over 25 is equal to 150 over 50 is equal to 3. So we'll get to what that means in one moment. All right, let's turn things around and look at what happens if we have it switched so that now our delta G, going from reactants to products, the delta G naught is a positive delta G naught. The activation energy in the forward direction is large, and the activation energy in the reverse direction is smaller. So go to our simulation. Let's reset this, and let's bring that up. I wish I had a little finer control on this. We'll bring that down. Now, as I put these in, think to yourself what you think is going to happen here. What direction is it going to be easier to go into? What direction is it going to... Oh, not 1,000. Yikes, 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 yikes. Reset. Let's try that again. 1,000 is too many. 100. Okay. I guess we could use 1,000, but that's just going to complicate things. So notice, it's taking a while to get anything into the B. I'm going to bump the temperature up. I don't know why. It says it's supposed to start off at 300 Kelvin. I want to get this temperature up. Otherwise, this is not going to happen. It looks like we're stuck. There we go. Now we're making some B. Oh, this is going to take a lot longer than I had hoped. This didn't take this long when I tried it a few minutes ago. I don't know what changed, but wow, this is taking a while. We got to get some of those B molecules made, so pump a little more heat in it. And we can remember heat increases the rate of the reaction, but increases the rate of both reactions. And we're going to talk about that in terms of equilibrium a little bit later on. All right, so you can see we're starting to make B molecules, but you notice it's a lot easier to make the B molecules react to reform A than it is to make the A molecules react to form B. So as we're watching it, it looks like we're trending back to, so A is trending down, we're in the 80 range, and if we waited long enough, we would get down to 75. So in the interest of speed, let's go down and write in that for A now, we have 75 molecules, 75 molecules, and for B, we have 25 molecules. So now the concentration of A is greater than B. And this is a reverse, or this is a reactant favored reaction. And there's actually quite a number of important reactions that are reactant favored, including the acid-base reactions that go on in your body. And we'll get to them in acids and bases. Because the concentration of A is bigger than the concentration of B, that means that the forward rate constant has to be lower, which makes sense because the activation energy in the forward direction is larger. What this means that it's harder in the forward direction, and so it's slower again in the forward direction forward when the concentration of A and B are equal to each other. And so having a large activation energy in the forward direction, that's going to favor the reverse direction, or the reverse reaction. And at the same time, we can see that the delta G naught is going to be positive. So having a positive delta G naught, it does mean that the reaction in the forward direction is not spontaneous, but at the same time, the reaction is going to be spontaneous, not in the forward direction, but in the reverse direction. So anytime you have a delta G naught that's positive, all that means is that if you put products in, you're going to get reactants. And again, that's when A is equal to B. Now, take my word for this so I don't have to go and run that demo again, that if we were to double the concentrations, we would end up with 150 A's and 50 B's. And again, I suggest you go and try that yourself so that you can be convinced that it works. Again, the concentration, here we go again. The concentration of B, why did one come down and the other come up? I don't get this. Let's try. B over A is equal to 25 over 75 is equal to 50 over 150, and now is equal to 0.33. So what's happened is we have a number here now, the ratio of the concentrations of B to A, the ratio of the concentration of the product to that of the reactants, that describes whether we are product favored or reactant favored. And we call that the KEQ, the equilibrium constant. Two guesses what EQ stands for. And this is a capital K, the equilibrium constant. And for these reactions, what we just drew, that A over B, is the equilibrium constant. So here, the KEQ is equal to 1. That doesn't favor either direction. In the second column, the KEQ is equal to 3. And because the ratio of B over A is bigger than 1, this is product favored. And in the third column, the KEQ is equal to 0.33. And because the ratio is less than 1, so this ratio is greater than 1, this ratio is less than 1, and a ratio being less than 1 is reactant favored. All right, you're with me, you stuck it out, we're almost to the end. So now, let's take a look at how the equilibrium constant actually relates not only the concentrations, but the rate constants of the forward and reverse direction. Again, as we said before, assuming that the reaction occurs in one step, we have the two rates of the reaction, and we're going to set them equal to each other down here. Now, when we set them equal to each other, what we're going to do is rearrange this equation so that we have the concentrations on one side and the rate constants on the other. So let's divide both sides through by the A, and let's divide both sides through by the reverse rate constant. And so what that gives us now is that the equilibrium constant, we can describe it two ways. It's the ratio of the forward rate constant to the reverse rate constant, or it's the concentration of the products over the concentration of the reactants. Sorry, that should be an A. And in fact, that's how we often write it. We often write it that KEQ is equal to the concentrations of the products over the concentrations of the reactants. Because after all, these two things should be relatively easy to obtain, and that we call the equilibrium constant expression. In the next lesson, we're going to actually plug some numbers in here and see how we can use this expression to find the equilibrium constant, or if you know the equilibrium constant, to find the various concentrations of products and reactants. All right, I hope that wasn't too bad. Thank you for bearing with me here, and time for the homework. See you next time in class.